The current source can be used as active load. Remember, load means it's a resistor and active means transistors behave as resistors. So the current mirror source can be used as active load, which means a resistor, right? So basically the current mirror source acts as an active load. We will build this idea of implementing the mirror current source as an active load to the desired circuit, to the circuit that we are really interested in 2 steps. So to do that, let us go back and look at the PMOS version of the current mirror source. So the PMOS version of the current mirror source says that we will bias the circuit from the top. So we have I reference connected to a transistor, for example, M3, that this transistor M3 is diode connected, where this M3 determine the bias and voltage for M4, and then that will give you the current IO. This current source may be used as active load in the differential amplifier. So let's show you how we can do that. Remember that the differential amplifier says that I will have M1 and M2 biased by a current source, and here is the input voltage Vn, which is the differential input voltage. Now these 2 transistors will give you an amplification at the output. So what we will do is we will say that the load at M2, whereas in this case will be single output differential amplifier, will be implemented as a current source. So the load at M2 is implemented as the current source, which is I reference connected to M3, and that is connected to M4, while the output of M1 is connected all the way to VDD. Basically, the current source is a load at the output. That's basically what we did. And now we are interested to find the gain. The gain can be expressed as the voltage gain AV will equal to capital GM times RO, and capital GM is the transconductance of the amplifier, and RO is the output resistance of the amplifier, looking at it from the output. Then we can define that GM, which is the transconductance of the amplifier, to be IO over Vn. Keep in mind that this is all AC signal here, so the output AC current over the input AC voltage is the transconductance, and we know that for this particular transistor the output AC current is basically will be GM1 times Vn over 2. Remember that GM1 and GM2 is the same, and then we're gonna divide by Vn, so you can see that the Vn cancels out, and that basically will be GM1 over 2. Remember, the AC current through the transistor M2 is given by GM times Vn over 2. We are assuming here half the voltages are applied to both input transistors. And that's very interesting. What it says is the transconductance of the overall amplifier is basically 1/2 the transconductance of the transistor. So now what we are interested in is solving for RO. To solve for RO, we apply Thevenin theorem at the load of the AC circuit. Then the current source is replaced by RO4, because looking back into the transistor of M4, we will only see RO4. And M1 is replaced by 1 over GM, and M2 is replaced by RO2. And that makes sense, because when you look up into M4, you're looking into the drain, so you're going to see RO4. When you look down into the drain of M2, you're going to have RO2 in series with looking into the source of M1, which is nothing but 1 over GM R1. So when we do that, we can see that RO will equal to 1 plus GM2 times RO2 times 1 over GM1 plus RO2 in parallel with RO4. So the way we did this is basically by the analysis, and the output resistance RO approximately equal to 2 RO2 in parallel with RO4. Then the gain is given as AV will equal to GM times RO, which equals to GM1 over 2 times 2 times RO2 in parallel with RO4. The way we solved for RO is by applying a test voltage and a test current. We skipped the steps here. You can easily verify it when you use the small signal equivalent circuit, and you will be able to get the same answer. The problem with the circuit is the current through M1 is going to waste, right? Because half of ISS will go through M1 and is going to waste, and in addition I'm using iReference to bias M4. The solution to this problem, to use the current through M1 to bias the current going through M4. So instead of using another reference circuit that biases M4, we're going to use the current through M1 to bias M3, then bias M4. So the circuit will look like this. Here is the differential transistors M1 and M2, which are biased through ISS, and they have Vn. Now when we go to the load, here is M4, but M4 is biased using M3, and M3 has the same current as M1. See, and this is a little bit clever because now we do not waste the current going through M1. We have to make sure that M3 is a mirror of M4 because you want to make sure that the circuit is as symmetric as possible. Then always I3 equals to I4, right? This is the requirement we have to have. Otherwise the circuit will deviate and you will have some problems, right? Because the current ISS must be split in half between M1 and M2, and then the currents through M3 and M4 should be equal. Then we have to say that M3 and M4 are mirror images of each other.